Without further ado, let me introduce the first morning speaker, Sami Murthy from King's College, telling us about black holes and their microstates. Thank you.
All right, thank you very much. Can everybody hear me in the back? Okay, I'll try to use this screen. I don't know, this will be on anyway. So thank you very much for the invitation. It's my first time in Sweden, and I've been enjoying it a lot so far. I should begin by congratulating the organizers for putting together such a wonderful and exciting conference. So far, it's been smooth sailing, and I know that that requires a lot of work. Also, I should say that I really enjoyed the poster session yesterday. All the posters were very clear, very professional, and very informative. So well done to all the participants. So I was asked to give a review on recent developments in black hole thermodynamics. Now, this is a large subject, and in fact, in the last few years, it's seen remarkable developments along different fronts. And I will be talking about a set of related subjects which I try to tie together in this title, Near-extremal black holes and their microstates. And I should say that there are other developments which I will not cover, both because of lack of time and because I don't feel particularly qualified to do so. Notably, the relation between black holes and operator algebras, and also about the dynamics of near-extremal black holes. Okay. So in the first 10 minutes, I'll try to give an overview. It's an hour's talk, so it might get boring. So please do interrupt. That'll make it more lively. I'll try to pitch it basic, at least in the first half hour. In the first 10 minutes, I want to give an overview. And because it's basic, I'm sure, because I know some of you, that many things I say will be well known to one or the other of you. So in which case, feel free to make advanced comments. That's also very nice. OK, so let's start. So what's a near-extremal black hole? So by that, today we mean this. Consider a black hole carrying mass and charge. Okay. We could also consider spin, but for most of the talk, I will not do that. Maybe I'll give some comments later. And all the statements I make applies to a large range of theories. But in order to be concrete, I'll take as a running example just Einstein-Maxwell theory. Okay, so general relativity coupled to one gauge field, and consider a black hole solution with mass and charge. When I talk about other theories, I'll try to say it explicitly. Okay, so this is a well-known solution, the Reissner-Nordström solution. And it has two horizons given by this easy formula. I've put G Newton to 1 here. And that's the temperature. The temperature is proportional to the difference between the positions of the two horizons. And it's clear from this formula that the mass has to be greater than or equal to charge. And when the mass when the mass approaches the charge, the two horizons approach each other, and the temperature goes to 0, and that's called the extremal limit. So when the two horizons are on top of each other, we'll call that an extremal black hole, and the temperature is 0. And when temperature is close to 0, we'll call that a near-extremal black hole. I should say that in the extremal limit, the event horizon radius is given by Q, so that's our parameter. And that also sets the scale. The curvature of the horizon is inversely proportional to Q square. So when I say something is small, when the temperature is small, I mean with respect to that scale. Now, why are we interested in near-extremal black holes? Now, there are many reasons. Maybe many of you have many reasons. Well, firstly, you could say, well, because they're there, we should study them as theorists. Here's the solution. They're also there up there in the case of spin. So there are spinning black holes, which carry a lot of spin, and they also approach extremality. Okay, this is this black hole survey that we've seen. Today, my reasons are twofold. So firstly, at very low temperatures, when the black hole is near extremal, quantum gravitational effects are enhanced. And we've learned in the last few years how to treat this quantitatively. Okay, we can do calculations. So that's my first reason. And secondly, one of the big successes of string theory is the explanation of microscopic black hole entropy. And mostly, not always, but mostly, that has to do with the situation that you discuss is always extremal or near-extremal black holes. So we want to revisit that in light of these new developments. Okay, these are the two things we want to discuss. Okay, now let's say t is small. So then instead of m and q as parameters, I could take q and t themselves as parameters. And you can ask, what's the area of the event horizon? That's the entropy. And you get this formula. Okay, when t is 0, the radius is q. So the extremal entropy is pi q square. And then you have corrections. So there's the first order correction in t here. I've put back L Planck. And then there's a systematic series of corrections. Okay. That's very easy to do. And you see here the appearance of a certain energy scale. And I'm going to call that 1 over E gap. Okay, so that energy scale I'll call E gap. Okay, that's set by the black hole. Any near-extremal black hole has such a scale. The details really depends on what black hole you're considering, but roughly it'll scale as an inverse power of the entropy. Okay. Now, this picture that I present here of the semi-classics has been the state of the art for many years until recently. But there's something about this that should bother us, and it has bothered many people, namely that it's very different from what we are used to in usual quantum statistical mechanics. So you have a large system, and when you take the temperature to 0, usually we expect that the number of degrees, the entropy, goes to 0. This is the so-called third law, in quotes, of thermodynamics. It's more of an expectation coming from quantum mechanics. That unless there's a symmetry underlying the system, there's one or a finite number of ground states. This can be made more precise, and in fact, this was done in this nice paper by Preskill, Schwartz, Shapir, Trivedi, and Wilczek back in '91. That something must give, something must go wrong at low temperatures. And roughly the argument is as follows. So when the black hole has high temperatures, then, so let's say it has some energy above extremality, and then you consider the process of Hawking radiation. So there's a small Hawking quantum that is emitted, and then the black hole will sort of decrease its energy just a little bit, but that process is essentially continuous. It's an adiabatic process. And so you can write the Hawking rate, and you can ask what's the decay rate, and then integrate this equation. Okay, that's what we learn in school. But when this energy becomes very small, at some point, it's going to be comparable to the size of the typical quantum of the Hawking radiation. And in that case, let's say it's twice the Hawking radiation, then emission of one quantum will drastically change the quantum state of the black hole. Let's say E goes to E over 2. Okay, so clearly the adiabatic approximation is not true. And moreover, if it's really small, you could also have quantum fluctuations. If you just naively do what we do at high temperatures, there's a Hawking quantum which takes you below extremality. You could emit something which is larger than the gap. Okay, and that of course violates all kinds of ideas and expectations from classical general relativity. Okay, so that was basically what the puzzle that was presented here. Okay, now what we've learned in the last few years is that this picture is dramatically modified. This picture is completely incorrect. Okay? And in fact, a near-extremal black hole is like an ordinary quantum system. And when temperature goes to 0, the density of states actually goes to 0. Okay? And the reason we've been able to make this kind of statement, the technical engine, is the discovery of a certain light mode, nearly gapless mode, which lives near the horizon of the black hole. Collectively, so it's a set of modes called the Schwartzian modes, which we've learned how to quantize. And so that's the driving force, the technical engine, that allowed us to make such calculations and such statements. Okay. I want to note that when Q is large, the horizon of the black hole is weakly curved. Okay, so the regular dimensional analysis will say that 1 over Q squared is small. Nevertheless, the quantum effects are large because there's a new scale which appears, which I hinted at, which was this E gap. Okay. It's a strongly coupled mode that appears. So today what I want to do is the first half, I want to just discuss what I just said. Okay, I want to explain what is this nearly gapless mode, what is this density of states, and what's the mass gap. Okay, the first half will be, many of you would have probably heard about this, but I thought it doesn't hurt to review it. Okay, review it from a point of view which maybe not all of you have seen. That's how I got into it, so that's how I'll present it. Then I want to discuss some consequences on supersymmetric black holes, on Hawking radiation, and if I have time, then perturbative string theory. And then in the last 20 minutes, I want to revisit black hole microstate counting and string theory, okay, in view of these developments. Any questions about the plan or the idea or the basic points? All right. So let's. Sorry, what time did I start? I'll just put a. I'm 10 minutes. Okay. Let's put a timer. Okay. So let's start with the nearly gapless mode. So how does this appear? So let's begin by framing the question. It's getting hot. So we often hear about the black hole Hilbert space. You would have heard these words. What do we mean? Different people mean different things, and it depends a little bit on the situation. But more or less, what everybody means is the following: that imagine a universe with some time direction at asymptotic infinity. So you have the notion of a Hilbert space, a Hamiltonian Hilbert space, and inside that you have a black hole solution. Okay, so consider such a situation and imagine there's only one black hole, and then we have this idea that there's an inside and the outside of a black hole, and this is the quantum mechanical analog of that the full Hilbert space factorizes into the black hole Hilbert space and outside. Okay, that's roughly what we mean. This is the zeroth order framing. So this is like what you would do when you have, let's say, a cold atom or a molecule, a bunch of things, and let's say they're separated from the rest of the environment. You'll say that's the Hilbert space, and then there's everything else, and there's a weak interaction. Okay. The difference, of course, is that the black hole Hilbert space has a huge dimensionality. It's equal to the exponential of the entropy that we just saw. All right. Now, what we want to do today is to ask whether this picture is correct. All right. Now, clearly when T is large, this picture is clearly wrong. It's at best an approximate picture. It's wrong because there's Hawking radiation. Okay, there's the horizon of the black hole, and there's quanta which is constantly being exchanged between the black hole and its environment. There's pair creation. So there's no sense in which you can say this degree of freedom belongs to the black hole and that one to the environment. Okay, and the correct description is clearly the canonical ensemble. We have a heat bath in which the black hole is in equilibrium. Okay. I should make a caveat here that if you go to, let's say, 2 or 3 times the event horizon size, and if you look at the potential which a particle feels when falling into the black hole, there's a sort of hump to the potential which is peaked around 2 or 3 times the black hole horizon size. And if you take your system, the inside of the system, to be that much of space, then essentially the gray body factor can be made very small. So there's radiation going out of the black hole, but if the hump is very large, then very little of it leaks out. Then more and more it becomes like a molecule or an atom, okay? Except, again, that it has a huge dimensionality. Okay. All right. Was there a question? No. Okay. Now let's see what happens when you take the temperature to 0. Okay. So in the semi-classical theory, so again, I'll work with this effective low energy theory. There's Einstein-Maxwell theory. So in the semi-classical theory, as we all know, the black hole develops a throat, a very long throat close to the horizon, and that's given the near horizon configuration is ADS 2 times S2, and the gauge fields take up has a constant electric field. Okay, that's the near horizon, and that's connected by a long throat to the asymptotics. Okay. And when t equal to 0, let's just do semi-classical physics. When t equal to 0, this near horizon geometry decouples in the sense that in its own right, it's a solution to the equations of motion. I could have never told you about the black hole and just said, consider Einstein-Maxwell theory, and that's your solution with good asymptotic boundary conditions of ADS2. Okay. It's fixed completely by the charges. Okay. And in particular, even when the theory is more complicated, like supergravity, when you have scalar fields, and there are asymptotic data which typically participate in the full solution, the near horizon geometry does not depend on this asymptotic data. This is the famous attractor mechanism of Ferrara-Kaloshin-Strominger. Okay? Very good. So that's the sense in which semi-classically the black hole, the near horizon black hole, is decoupled from the environment. Okay. Now, the question we want to ask is this true quantum mechanically? Because I'm trying to make the question more and more precise. Is this true at the quantum level? Okay. So the way I'm going to answer this question is as follows. So what could go wrong? Well, I said that when you take t goes to 0, there's this long throat which attaches the near horizon and infinity. Now, there could be degrees of freedom in that throat which don't quite decouple. That's the main idea. And the point of view I'll take is not to postulate any type of degrees of freedom, but instead work from inside the black hole. So I'm going to take this point of view that semi-classically, there is this ADS 2 times S2, and now I'm going to quantize this system. Okay, this is a point of view which was proposed by Ashok Sen about 15 years ago while trying to calculate quantum corrections to this black hole entropy. Okay, so the idea was that you have this ADS2, let's think of ADS2 CFT1 and try to quantize it. Okay, so how would you do that? You have ADS2 boundary conditions, ADS2 times S2, it's a 4-dimensional theory, and you have all the fields of gravity, and then you have to put some appropriate boundary conditions on ADS2. That is well known by the rules of ADS-CFT. What are the fall-off, what are the decay conditions to put? And then you have these fluctuations, and you have to integrate over all this field space with the action of gravity or supergravity or what have you. Okay? So almost all of these modes, when you do this kind of path integral quantization, almost all of these modes, the action of these modes, which are off shell, are given by set by the characteristic scale of the black hole, which is just Q. Okay, so that's how you do that. Now, the subtlety is that, in fact, that is not quite right. There are there's one family of zero modes. Okay, so just by the effective action, I just mean Einstein-Maxwell theory. When you quantize this, what you find is that there are always these set of so-called pure gauge modes. So this is just harmonic analysis on Euclidean ADS 2 times S2. This is a very nice article by Camporesi and Higuchi. They do harmonic analysis on ADS space and spheres, and you can put it together. And what you find is that while in higher dimensional ADS2, they write down what all the harmonics are. For ADS2, there is something very subtle, namely that there are these pure gauge modes. So what does that mean? So imagine ADS2 written like this has the hyperbolic disk. So rho is the radial coordinate with this kind of metric. Then you consider a coordinate transformation, a diffeomorphism, which asymptotically looks like this. Okay, it's labeled by integers except 0, plus, and minus 1. Okay? So it's some kind of coordinate transformation that you do here. And then you ask, what's the corresponding gauge field, in this case, the metric. Okay, so that's the usual formula that you would write. Now, if you've not seen this before, you should say, why are you considering this? Of course, there are gauge transformations, and we always throw away pure gauge modes. Now, the problem is that because the space is non-compact, there's a normalizability condition that you need to put. And these gauge modes are not normalizable. Here, I wrote to you what the gauge mode is close to infinity. You can see it's a constant, and therefore it's not normalizable. Okay, it goes as e to the I and tau. Tau is the time direction. Okay, but when you differentiate it, then that gauge field or the metric is normalizable. Okay, so another way to say it is that if you think of the gauge parameter as the ghost is not present in the spectrum of the theory, but the gauge field is, and that makes it physical. Okay, the ghost does not run in the loop to cancel it. Okay, however, because formally they're pure gauge, the action is 0. Okay, that's the reason why there's 0 modes. Okay, these are physical 0 modes of the theory. Okay, you can write it in a better way. You can collect all these modes into one field, which I'll call epsilon as a function of tau, and then write down what this is in terms of this one-dimensional field. Okay. Again, I emphasize that these 0 modes are physical, and in fact, they've been used. So in the past, in this whole program of Sen, while quantizing the fluctuations inside ADS2, you had to countenance this. So you say, how do I do that? Well, at that time, we didn't know how to do it. So you assumed, so what do you have to do? You have an integral over these parameters epsilon, or this field epsilon, as part of the integral over the metric fields. But the action is 0. So what you're calculating is the volume of field space. Okay, that's a hard problem. We don't know how to do that. It's ill-defined. And at that time, what Sen did was to say, well, let's assume that this volume is finite, and then ask, how will it change if I change the size of the black hole a little bit? Okay? And that is a tractable problem. You can use arguments of ultra-locality of the measure due to Witten, and you can calculate that. What you get is some kind of correction like this, logarithmic corrections to the extremal entropy. So e to the pi q square plus this coefficient here, which I'll call C log times log q. Okay, so that was calculated, and that has been used. It was also used in other methods, like you can use localization to calculate the quantum entropy, and these zero modes are also important. Okay, so it's definitely physical. Okay, any questions about this? All right. Now, now we're faced with this. We want to say, okay, there is this volume, but now we can't just throw it away. What if the volume is 0 or infinite? Then the whole problem becomes ill-defined. So we want to do this correctly, and the way to do this is to regulate it. So we give a small temperature, just heat up the black hole a little bit away from extremality, and solve the equations of motion. So the near horizon configuration looks like this. There's this radius 2 times S2, and there's a linear correction in temperature and higher orders. What does this look like? Well, the leading contribution here, it looks like this. So this is the radius 2 times S2. When t is 0, the sphere has a constant radius throughout radius 2. This is the extremal attractor radius 2 times S2 we're used to. And what this perturbation does is it changes the size of the sphere, and it grows exponentially towards the boundary, okay, with coefficient t. Okay. Now, this should already tell you that something is funny, in the sense that this, by no means is this a good sort of system to consider. You can't put boundary conditions here if your perturbations are growing exponentially. Okay? But what we can do, and that's what we'll use it here, is to use this as a regulator. We'll turn on a t, we'll study the quantum fluctuations of this mode, and then take t to 0. Okay? It's a bit like how we study magnetization, right? Spontaneous magnetization. You have to put an external field, ask how does the system react, and then take the external field to 0 and ask what remains. Okay, that's the idea. Okay, so that's the metric has changed. And now, of course, the semi-classical entropy takes this form, which I showed you in the first slide. Okay, so that's the appearance of E gap. And now you begin to see the meaning of E gap, the significance of this E gap. So these zero modes of pure radius 2 times S2, which we just discussed in the last slide, pick up a t depends. The action of these zero modes is no longer 0, because now there's a linear term here. So you'll have a term which is like, let's call the zero modes H, like we did. Then there is a GHH type of coupling when you write the action. And that gives you the first order quadratic correction. Okay, so what you get is something like this. You get that the Einstein-Maxwell action picks up of epsilon of this sort of, nearly zero mode has this form. Okay, it's proportional to t because of this background t. And then it has this certain shape. This is a quadratic, quartic in the derivatives. Okay, and you begin to see. So now you might recognize this. So let's make some comments. So this is the thing we'll study a bit. So firstly, you see it's strongly coupled. So when t goes to 0 in units of E gap, okay, the coupling clearly becomes very large. So that's what it means to be nearly gapless or strongly coupled. So that means the quantum fluctuations are very large. And this is the action that essentially controls the coupling of the black hole to the asymptotic region. Okay? Now, when you turn on t, like I said, the whole metric changes. And when you go here, it goes wild. So there are many operators that couple the near horizon and the asymptotic infinity. But most of them in the near horizon were massive. They already had a large energy. Okay. So the correction due to this t will be very small compared to what was already there. So there's a smooth limit. Okay. But it's these ones which had zero action, which now pick up a small action. So this difference is going to be enormous. Okay. So this is the, let's say, the leading is the dominant coupling that controls the coupling. Okay. Any questions? Very good. So that theory, sorry, I should have said, of course, that it might be familiar to many of you, is precisely what is called the Schwarzian theory. Okay? This may not be how you've seen the presentation. Okay? Typically, you might have seen some effective two-dimensional theory, the theory of Jakob-Teitelbaum gravity, which is some dimensional reduction, and then you sort of ask what's the correct boundary condition. So this is a way to do this intrinsically from the near-extremal black hole. But you can actually just do a change of coordinates. We wrote this in this paper to get back to what you might have seen. This is the picture which I think most of you have seen. So in the picture I presented, the boundary conditions were fixed, okay, of all the fields, and the metric changes when you turn on T. An alternative presentation is that you insist that the metric is always locally ADS2, but the boundary conditions change. So this epsilon mode that I showed you can be put equally into a wiggle of the boundary. So you said that the boundary has fixed length, but its shape is not fixed. Okay, those two are completely equivalent by a certain coordinate transformation that I'm not writing. You can read this paper. All right, and in this way of writing it, it's sort of very geometric. What is this mode? This is essentially diffeomorphisms of the boundary. So there's a circle, so there's time reparametrization invariance symmetry at the boundary. And the ADS, so the theory has that symmetry, but the ADS2 solution breaks that symmetry. But the ADS2 does not, you can't change time, you can't reparameterize time at ADS2. So the ADS2 breaks that symmetry. So this is like spontaneous symmetry breaking. Okay. But ADS2 has isometries. It has SL2 isometries. The easiest one we know is just the rotation of the disk. That's L0, and then there's L+1 and L-1. So those are not part of the spontaneously broken modes. Okay, so the system that we're studying is diff of S1 quotient by SL2. Okay? And this action, this Schwarzian action that we saw, geometrically describes the motion of this coset. Okay. I'll come back to this. And in the last 5, 6 years, actually going back to 10 years, there have been many different methods that we've learned to solve this theory. As I said, most of them have been through this two-dimensional JT gravity, but essentially you have to solve this one-dimensional theory. And there are many methods. There's a nice review by Mertens and Turiachi, which you can read. And the result is that this theory is one-loop exact. Okay, so you can write the one-loop partition function, and here I gave you the answer. Okay? In fact, this is quite easy to, if you just want the one-loop calculation, you can essentially just argue it out. The reason is that, so think of what you want to do. What you want to do is to integrate over epsilon, so you have all these modes of epsilon, okay, with this action. It's some quartic action. That's not very easy to do a priori. But if you just want the one-loop result, then you can use ultra-locality. So you say that at high energies, the measure, the Gaussian measure, is such that the integral of the field itself is 1. Okay, that you have to put some condition of that sort. And what we want is the integral over all the fields of all the modes of the field except SL2, except 3 modes. Okay, so the answer is 1 divided by the integral over those 3 modes themselves, but each of those 3 modes are just bosonic modes, and it'll pull down a 1 over square root of t because that's a bosonic mode, and therefore when you divide by it, you get t to the 3/2 in the numerator. Okay, so it's as simple as that. You can also do it by more sophisticated methods. Okay, so that's the one-loop answer, and now I said that. So this theory is one-loop exact, and so that's why I gave you this. Thank you. Any other comments, questions? Yeah. So one-loop exact is not so easy to argue, but it's still true. Good. So now we want to put this all together. So here's the extremal entropy of the black hole, pi q squared. These were the first corrections, semi-classical corrections. These were the logarithmic corrections to the extremal entropy. And now you have here this T over E gap to the power 3/2 as a prefactor to the partition function. Okay. And the notable thing is, although it multiplies something very large, it goes to 0 as t goes to 0. Okay, so that's what gives the dramatic change. So here is, so if you give the partition function, you can read off the density of states using a Laplace transform, and this is what it looks like. So for large energies, so this is the density of states versus energy above extremality. So large energies, the dotted line is the semi-classical curve. So it goes like that, and then it hits this semi-classical result of e to the pi q squared times the one-loop correction. And then you see that at large energies, it essentially follows, the quantum curve essentially follows the semi-classical curve, but at low energies, set by the scale of E gap, there's a dramatic change. And in particular, when you go to t equal to 0, then the whole density of states go to 0. Okay. Yes. Yeah. Can you shout? Yeah. Yeah. Yes. Yes. Yes.
By what some of us had explored,
Yes.
in addition to doing the one-loop Schwartzian localization by
Yes.
Stanford and Witten.
Uh-huh.
But strictly speaking, that's a disk path integral result
Yes.
where there's literally one
multiple.
boundary.
Mm-hmm.
And within the limit where you have just one boundary, then you can take t to 0.
Yes.
But however, there's a catch. If you want to consider the full path integral,
Yes.
one cannot take that limit t to 0 because there would be non-perturbative effects because of loop corrections and higher genus corrections, which are exponentially small in the black hole entropy.
Yes.
So in that sense, strictly speaking, t to 0 limit is at this level we cannot do because this still is exploring a certain energy level above the ground state. So do you have any perspective?
Absolutely. No, so I would just repeat. So firstly, I hope I refer to the right paper of yours, somewhere here, over there. I don't, if it's something else, you should tell me. But it's a very good comment, which is that, I'll just repeat it. I'll repeat what Upo said, which is that I've been a little glib when I say t goes to 0, because these are perturbative corrections, okay? And there can be non-perturbative effects. Okay? And so very, very close to here, you should stop trusting it. Okay, so somewhere here, so when you have t between E gap to the exponential correction, which is e to the minus the entropy of the black hole. So this is 1 over the entropy to some power, but here you have e to the minus entropy of, right? When you have, let's say, it's the scale of energies where you have 1 or 2 quanta. There you should stop trusting the result. Yeah, did I summarize the comment correctly? Thank you. Okay, that's a very good comment, and in fact, thanks for I should have said that, thanks. Okay. Other comments, questions? All right. Okay, so here you see this. By the way, this plot is from this paper. So this whole, if you want to sort of see this development with Luca Liesiu and Joaquin Turiachi, we wrote a paper in 22. We wrote 2 papers. One is called Revisiting Revisiting Logarithmic Corrections. All of this is contained in that if you want to read it in detail. This plot is from this paper. And now we can repeat this for supersymmetric black holes. And for supersymmetric black holes, so here I should say that the semi-classical intuition is strongly corrected. For supersymmetric black holes, in this throat region, you have more light modes. Because you have supersymmetry, you have supersymmetric partners of the Schwartzian. So you have to quantize the whole system. So there's the Schwartzian modes, the SL2 modes, there's fermionic superpartners, and also bosonic superpartners. There's a bit of a story here, which I will not tell you unless you're interested later. But roughly speaking, there's an exact cancellation between the bosons and fermions. And instead of t to the 3/2, you get t to the 0. You get 1. Okay? So for supersymmetric black holes, the naive semi-classics plus sort of extremal loop corrections is correct. Okay, so now it looks like something like this. Okay, when you draw the density of states. So again, that's the semi-classical picture is the same for supersymmetric and extremal black holes. But now the quantum density of states is completely different. So here it follows it, and then instead of going to 0, at 0, there is all the states of the black hole. So that's what, this is like a delta function, that's what I mean by this. And then there's a mass gap, there's an energy gap, okay? So another way to, one sort of slightly loose way of thinking about it is that semi-classically, there's a lot of states near the horizon of the black hole, but quantum mechanically, these states sort of spread out, because of perturbation theory, spread out and merge into the continuum. That's for the non-supersymmetric black hole. Okay, this merge here. While for the supersymmetric black hole, they really clump up exactly at 0 energy, and then the continuum begins after an energy gap. Okay, so this is important because now it means that this supersymmetric black hole is actually decoupled from the environment with a gap. Okay, this was one of the worries which people had long ago when Strominger and Waffa first wrote this. But at that time, it was sort of such an advanced question. People are just beginning to find the matching that it took a while to understand this. So you could ask in the Strominger-Waffa calculation, there's some microstate counting of BPS states, and then there's a BPS black hole. But if the black hole is not decoupled, then you should not really think of it as an independent quantum system. Okay, so is that really true or not? And now we see with these calculations that indeed the supersymmetric black hole can be thought of as an independent quantum system. Okay, so that finishes the first half of the talk. Any questions or comments? Okay. Then let's move on. So now I want to flash some applications, and now I'll change style a little bit. Instead of a development, I want to show you some snapshots. Okay. So I don't expect everyone to understand everything, but ask questions, or you can also ask me questions later. Okay. So there'll be 3 applications I'll give. The first one is to the exact entropy formulas of supersymmetric black holes. Okay. So 12 years ago, Ashok Sen had started this idea of trying to calculate quantum corrections to the entropy of a black hole. And we had pushed it to using methods called localization to calculate all quantum corrections. Okay. Of course, now because of this decoupling of the black hole that has been put on a solid footing, but in fact, there is a little more that the Schwarzian is useful for. So the way this went, I'll give you a very brief snapshot, is that you had some microscopic counting. This is called d micro in string theory. There's a number of states, there's an integer. And using methods from analytic number theory, this is the type of thing Lawrence was discussing yesterday. It's called the Rademacher expansion. There's a way to write this as an infinite series of analytic functions. Okay, that's a Bessel function. Okay. And now the idea is that you think of this ADS2 CFT1, and this is really the partition function of the black hole, okay, of the ADS2 black hole. Now we want to interpret this. You want to check whether this is true. And that's what we've done. And basically, this part of the formula you could derive from this all-order fluctuation analysis that's using some localization, lots of methods. In fact, there's a whole many works here. And that you can, using that, you can capture this. The sum over C itself, I should have begun with this. The sum over C itself are interpreted as orbifolds of ADS2, some ZC orbifolds of ADS2. And you see that the Bessel function asymptotically goes exponentially. So higher C is exponential corrections. Okay, so that's that. And here, there's this thing is called the Klosterman sum. We also saw that yesterday. It's a sum over phases, and that also could be accounted for by certain Chern-Simons theory on this orbifold. And I've divided, then what remained was a power of C. C is just this number. And I've divided it into 7, it was 9/2, and I divided it into 7/2 and 1 over C to show that actually this part is actually the one that's captured by the localization. At C equal to 1, you can't tell because it's 1. But it turns out that what was missing in this old analysis was this 1 power of 1 over C. And that's exactly what we find is the volume of the space of this super Schwarzian on the orbifold. Okay? So I just wanted to flash this to tell you that this Schwarzian is actually doing some job. It's not just some philosophical thing which helps you to say that it's decoupled. Okay? So it's a very tiny contribution. Okay, another contribution, the second, I'll call this 1B application is the following. So the context is like this. So consider this ADS2 times S2. So these are 4-dimensional black holes. These are spherically symmetric, and they have 0 angular momentum. Okay. Now, by spin statistics, 0 angular momentum means 0 fermion number. Okay. Now we think of this black hole as an ensemble of quantum states, as a collection of quantum states. Okay. And the statement in supergravity that this black hole has 0 angular momentum means that on an average, this ensemble has 0 angular momentum. Okay, that's what gravity is like the average. But now you run the rules of ADS CFT, and you find that at the boundary of ADS2, if you think of any gauge field, there's always 2 legs. And in 2 dimensions, the order is flipped. It's the field strength that dominates in 2 dimensions rather than the potential, unlike higher dimensions. So the natural ensemble here is microcanonical. So that means you have to fix the charge. Okay, unlike higher dimensional ADS where you fix the potentials. Okay. Now you put these 2 statements together. That on an average, the charge is 0, but every state in the ensemble carries the same charge. That means that every state has charge 0. Okay. So that means that every state is bosonic. Okay. So this is a vanishing theorem that we had developed. And what it means is that trace of -1 of the F is actually equal to trace of 1. Okay, so we developed this about 15 years ago. And now the new thing is that because now you have the Schwarzian mode, we missed this zero mode, you have to repeat this argument. I won't show you the calculation, but you can do that. And again, using this density of states, you can show that only J equals 0 contributes. Okay? So this Schwarzian, if you want, is like something like a skin of the black hole. It's a very thin layer sitting on top of the black hole, but it's very floppy. It's the one that connects you. And because it's very floppy, its effects multiply everything that goes on in the bulk. Most of the entropy and all these arguments comes from the bulk, but there's a small contribution that's very important. All right. The second application is to Hawking radiation. In fact, this was the first puzzle that that I presented you with. So these are plots from this paper, and Luca kindly gave me these plots that I'm allowed to show. I mean, it's from the paper anyway, it's published. So this is a plot now of the rate of Hawking. So dE over dt d omega as a function of omega. Omega is the frequency of the scalar of the field that is emitted. Okay? And so they call what I call E gap, they call E breakdown, E break. And when the initial energy of the black hole is large, 100 times the E gap, then you basically are very close to the semi-classical picture. But in the quantum regime, when the initial energy is 0.1 times the gap scale, there's a huge correction. There's a very strong correction, exactly like we saw for the density of states. Okay? So the Hawking radiation formula, semi-classical formula would be this, but that's completely incorrect. And instead, this quantum correction goes like this, and it stops. And that's very important. That's the fact that saves you from going. This puzzle that was seen by Preskill et al., this is the thing that allows you to evade the puzzle. Okay. There we go. Okay, so it affects the low temperature radiation and resolves this paradox. Okay, you can also do, so I call this 2A, and 2B is the opposite of it, which is instead of Hawking radiation, you can ask about absorption. You take a black hole and throw something in. You can ask, what's the cross-section of absorption? Okay. So at very low energies, if I have an extremal black hole, and I throw, let's say, a scalar wave at very low frequency, then essentially the absorption cross-section is the area of the black hole. Okay, this is well known. So that's this black line. And the red line, these are plots from, so I should say there's lots of works here. Roberto Emperan, Anna Biggs, Emperan Trezzi, who's here in the audience, and he had a very nice poster yesterday about this, and also this paper. So these red lines are the quantum corrected curves, and as you go close to extremality, you actually go upwards. It's slightly counterintuitive that the absorption cross-section increases. So the density of states inside the black hole actually decreases. So that's one effect of the Schwarzian. But in fact, the absorption, so transition amplitude itself is also affected by the Schwarzian, and that's affected in a positive way. So these two things play off, and in fact, overall, you get an increase. So that's one point. And the other point to note is that there are these kinks. I'll just check the time. Okay, let me just explain briefly why these kinks come. I should have said something long ago. So here, when we saw these pictures, so that was the semi-classical. Here I showed you the overall density of states, but you can do something slightly more refined. You can ask, what's the density of states for a field of a given spin? Okay, it turns out that there is a classical gap, which is J is the spin, J times J plus 1. So this is spin 0, it starts here, and then spin 1 starts like that, and spin 2 starts like that, and so on. Okay, there's a gap. While for the supersymmetric black hole, there's an intrinsic gap even for the spin 0, and then there are further gaps because of the spin. Okay, so why I said that? It's because that explains these kinks. Sorry about this. There we go. So these kinks are precisely when you hit one of these new spin modes. It's like a new channel of scattering or absorption. Okay. So that's that. Here is scattering in supergravity. You see that now there are lots more channels because there are more fields. Okay. Here is a plot of the probability of absorption when the initial state is the BPS state, is the extremal state. Okay, and now you see something interesting. You remember that for the BPS black hole, there was a mass gap, there's an energy gap, and therefore if you send a scalar or a wave of very small energy, less than the gap, then it should not absorb because it's by the Fermi rule. And indeed, you see this gap also in the absorption probability. Okay, so this is called quantum transparency. Okay, I'll move. Okay, I've done 45 minutes. I'm going to skip this. I'll just flash what the other, there are many other things I just thought I'll give you, but I'll give you the keywords and you can ask me later. So one of them you can ask is, I won't have a discussion. One of them is, okay, all this Shortian was a discussion in gravity. What happens in string theory? Okay, so in perturbative string theory, so that's one question. You can ask which superalgebras, this might be of interest to many of you here who study string spectrum and so on. You can ask which superalgebras arise. You can ask, so the discussion so far was close to the black hole. You can ask what happens to the Schwarzian modes far from the black hole. And then you can ask what happens when there is spin. And there's some interesting comments, but I want to skip this in view of time and move to the next topic. And later we can come back to that if you want. Okay, so now I want to sort of switch gears and discuss supersymmetric black holes in string theory. Let me pause if there are any questions about what we discussed. Okay, spin, let's postpone spin to the questions. So that was one of the things. It has been, so very briefly, so it has been, you can repeat this kind of analysis that we did also for spinning black holes. But there's actually something you have to, let me make the comment. You have to be a little bit careful because there's this classical superradiant instability for spinning black holes. And later I can show you, can quickly derive on the board, but roughly speaking, what happens is that unlike charged black holes, where the Schwinger decay process is exponentially suppressed, for spinning black holes, the superradiance of this decay process is not suppressed, and therefore you have to ask, how do they compete? And it turns out that they compete, the time scale of decay is comparable to the Schwarzian time scale. So the classical effects actually tend to drive you away from extremality. You can do the calculation, but this is really what happens. Okay, I can tell you more about that. Good. So supersymmetric black holes, good. So what's the usual picture? Usual picture is that you have this supersymmetric black hole, and then you have this set of microstates. Okay? They both have the same charges, and you do some counting here, and you calculate the area here, and then these two are related by some tuning of parameter of modulus, which we can call G string. Then everything is supersymmetric. Okay. Now, because now we have understood that this black hole decouples, and you can really think of it as an independent quantum system, it allows us to start asking really detailed questions. Okay, and one of the questions I want to discuss today is something, again, which was in everybody's head from the very beginning, but somehow hadn't been spelled out fully, which is that the way, what is done in string theory is this. Okay, so you start with this picture, you calculate the area of the black hole, maybe with quantum corrections. But on the microscopic side, what you do, you don't count the number of states, you count the supersymmetric index. That's the number of bosons minus the number of fermions. Okay? And these are the two things that agree. Okay, beginning with Strominger-Waffe and all the calculations ever since then, okay, in this game. So the question is, why does this work? You're comparing two different things. Okay, is it only an approximate agreement? Now, for a single black hole, you can make an argument to show why this agreement happens. And it goes like this. So these are the two things I already discussed. Firstly, that the supersymmetric black hole is decoupled. There's a notion of Hilbert space of a black hole and outside. And now, if you start with weak coupling and calculate the index, that index is protected as you go to strong coupling. Let's imagine there's nothing else outside the black hole. So that index really becomes the index of the black hole. But then we had this other argument that the index of the black hole is the same as the degeneracy of the black hole. Okay? And you put all these things together and argue why the index, weakly coupled index, equals the black hole entropy of supersymmetric black holes. But it's a bit long-winded. And you can ask, is there a direct explanation from the asymptotic theory? Okay. Now, so far in this discussion, there was an implicit assumption that, in fact, there's nothing outside the black hole, but that's not the case. You can have other configurations, which is not just one black hole, and in fact, they're well known. There are supersymmetric black hole bound states. Okay, so imagine this has charge gamma 1 plus gamma 2, and now you have gamma 1 and gamma 2, two black holes with charges gamma 1 and gamma 2. Okay, this is discussed a lot by Denef and collaborators. And in all cases where we can calculate the microscopic index, where these configurations also contribute, you can check that the index also accounts for that. Okay, in particular, there's a nice series of works by Matt Scott, Piolin, and Sen, which shows how to calculate that. Okay, so you really know that starting from infinity, you have a black hole saddle point, but you also have these multi-black hole saddle points. Okay, but now if you want to decouple, you're in trouble, because if you decouple the two black holes, suppose you, like this, you say, I'm going to zoom down the throat of this, there's some ADS2, you can do all that, but you lose sight of the bound state. You lose sight of the other black hole has gone off to infinity. That's not what you want to do. 5 minutes, okay. All right, thanks. So you want to ask, can I put all of these things inside one path integral, okay, or inside one accounting framework? Okay, and the new picture is that there's a direct way to define the index in the gravitational theory. And again, you use the temperature as a regulator. Okay, and this is the relation with the first half of the talk. And in fact, this is what Witten had originally done when he defined the index. You have some quantum mechanical system. You write something like a thermal state, e to the minus beta h. Beta is not 0, because only then does the trace converge. And then you put a -1 to the f to ensure cancellations. And so you have to use a beta to define the index, and the answer is beta independent. Beta is the inverse temperature. Okay? So we want to do something like that in gravity. We don't know how to do that with the trace, so we're going to use path integrals. So this can be converted to a path integral. It's just you have a time circle, you give periodic boundary conditions to the fermions. Okay? So in gravity, you can do that. You can study the analog of Gibbons-Hawking with periodic boundary conditions for the fermions around the time circle. And the question is, what are the saddles? So this is what I call the gravitational index. Okay? And the question is, what are the saddles of the gravitational index? Okay. Now, the fact that the microscopic entropy equals microscopic index equals the entropy of supersymmetric black holes might lead you to think that the saddle of this is the supersymmetric black hole. Okay. However, that cannot be the case for two reasons. So in gravity, when you give some temperature circle like this, you expect a solution of this sort. There's some contractible circle, okay? And where it contracts is the horizon. But supersymmetric black holes are extremal. They don't have beta finite, they have beta equals infinity, and correspondingly, the throat, there's an infinite throat in the interior, which we just saw earlier. You can even try to ask, suppose I start with the finite beta and impose an extremality on the solution. People have tried that, and you get some incompatibility. You either get a singularity or you get zero entropy. So that's the first problem. And the second problem is that this kind of cigar topology, which we expect from a Euclidean black hole, admits only one smooth spin structure, which is anti-periodic. That's the opposite of what we want from a supersymmetric situation. Okay. All right. Now, the resolution is as follows, that there's actually a family of non-extremal supersymmetric configurations in the Euclidean theory. And the way you construct it is as follows. So firstly, at infinity, you turn on a holonomy for an R-symmetry gauge field, okay, equals 2 pi I. So what this does, by definition, R-symmetry charges bosons and fermions differently. Okay, so that mimics for you the -1 to the f. So now you can put smooth boundary conditions, smooth conditions, spin structures for the fermions. Okay, so you've converted the fermionic problem to a bosonic problem. Okay, now you want to solve the equations of motion of supergravity with this boundary condition. Notice that this is complex, this is imaginary, so the solution in some way will be complex. Okay, but you can find such solutions, and there's a real slice along which this is smooth. It has a cigar-like topology and a non-zero, I call it temperature in quotes, because it's a Euclidean complex solution. And the extremal supersymmetric black hole is recovered in the t goes to 0 limit. Okay, so this is the same type of philosophy that we were using in the first half of the talk, but now applied to the extremal black holes. Okay, and the sort of miracle, if you want, is that if you calculate the Gibbons-Hawking free energy of this gravitational system, you find that that's exactly equal to the free energy of the extremal black hole. So it's independent of beta. Okay, so that's exactly what you would expect from an index. It's a smooth solution with some beta, with the correct fermionic boundary conditions, and the answer is independent of beta. Okay, that's the kind of thing which is the analog of what we're used to for the Witten index. Now, this was first done here in ADS5, but then it was repeated in all ADS spaces and also flat space. One comment, very quick comment, is that these are allowed by the so-called Kontsevich-Siegel-Witten criterion. I don't want to discuss that because of time. Maybe a couple of more slides and I'll stop. Okay, I thought I'll give you one example because it's nice. Instead of ADS5, the simplest example is back to Einstein-Maxwell theory. So this is kind of fun, so I thought I'll say it. So you want to write down a supersymmetric solution, and this is known for a long time. And it's given in terms of two harmonic functions, v and v tilde. And this is the metric. And you see that there's a rotation parameter in the metric. And there's also gauge field, there's an electric monopole, and a magnetic dipole. Okay. When v equals v tilde, the rotation goes away and the dipole goes away. The solution becomes extremal. This is the Reissner-Nordström solution when v equals v tilde. Okay. And now, if you take the two harmonic functions to be two sources with charge q by 2 and q by 2, there's a half here because of this normalization here. What you've done is you have a double pole solution for the extremal black hole with charge q, and you separate it into two single poles of charge q by 2 and q by 2. So I call it the north pole and the south pole. That's what gives you a dipole. And then you have to do a Euclidean continuation. I mean, that's T is the Euclidean. And you can do it either by recognizing that it's a Kerr-Newman solution and demanding smoothness at the tip, or by saying that, look, there is this source means that there is a Dirac-Misner string, and that has to begin and end smoothly at the poles. So in either way, you can do that, and what you find is that the angular velocity of the black hole equals 2 pi I over beta. Okay? And what that means is that the index is, according to Gibbons and Hawking, what you're calculating in the solution is trace e to the beta omega j to the minus beta h. That's what a GR person would do. But now beta omega is 2 pi I, so you have e to the 2 pi I j, which is precisely minus 1 to the f. Okay? So that's the sense in which these solutions give you indices. And now you can repeat this in many different contexts. So you can do it in 4-dimensional flat supergravity. So you have these attractor black holes. Now they become rotating black holes. You can do it in 5-dimensional asymptotic flat supergravity for black holes, black strings. So there's a lot of work in the recent years. You can do it for multi-center black holes with the same boundary conditions. Each black hole now becomes a little dipole. And now you can study its moduli space. You can study wall crossing in the path integral. You can study 5-dimensional black hole bound states. You can study black rings. This is some work in progress. This is really brief snapshots. In all these cases, the point I want to make is that you have some temperature at infinity, and all of these are non-extremal saddles which belong to the same path integral at infinity. Okay, so I'll stop here. Maybe I'll just flash this and stop here. Thank you very much.
Thanks a lot, Samir. So we still have time for a couple questions.
Arkan.
Just to clarify the logic about the first box. So you were mentioning that ADS2S2 is special, and that's a 4-dimensional black hole. But then you quickly mentioned Strominger-Waffa, which is 5-dimensional.
Yes. So maybe, sorry, I should have said this. I thought I said this. So all the statements that I made apply to near-extremal and extremal black holes of all types. I just took the Einstein-Maxwell theory in 4 dimensions as a concrete illustration. So you can take 5-dimensional black holes, you can take ADS2, with the near horizon always has an ADS2 times a compact factor. That's the only thing that's the same. Yeah, but near-extremal black holes of all types, near horizon, always develop an ADS2 factor. That's the only thing I've used here. And thank you very much, Arkady. I should have made this absolutely clear. So everything I say is not only for the Reissner-Nordström black hole, but for any extremal black hole. Because after all, the only thing I use is the appearance of ADS2. Thanks.
I have a quick question. So you emphasize that this Schwarzschild mode affects the logarithmic corrections to the entropy, but somehow it's not the whole contribution. Could you quickly comment on the other contributions to the logarithmic corrections?
Wait.
So you had this power of Q to the C log.
Yes. So that was the thing that you and I know very well from
the
the
that it came from the volume of the gauge mode, but somehow this is already encountered.
No. Sorry, let me just go back to the formula. Sorry. Here it is. So let's go here maybe.
Exactly, that's that slide. Yeah.
Here. So this was already present in the extremal black hole. It's not the volume of the zero modes of the gauge field. This was. Sorry. So let me clarify. Thanks. So the way I presented it, I separated the zero modes and the non-zero modes. But then I did something which, for ease of presentation, which is that here there's no Q. But in fact, there should also be a factor of Q here, because the zero modes, as you say, also contribute to a T-independent answer. I have rescaled the theory such that all the Q dependence has already gone here, and then you get that. So that comes out of the usual type of calculation of the loop calculation that we're used to. So that you can almost think of it as dimensional analysis, and then you're left with this thing.
Thanks for the clarification. I don't see any further questions. Let's thank Samir again for the beautiful
Thank you very much.